Hey, this is Professor Cummings, and I wanted to continue my machine design or kinematics, um, series that for this semester. And I have another example that I wanted to use today, and this one again is rotational analysis, and it involves a handsaw. All right, so if we look at this, let's go ahead and read what the problem is. Initially, the motor on the circular saw turns its drive shaft at 20 t raised to the 2/3 radians per second. That's omega of the motor is going at this angular velocity. So radians per second. So again, that's rotational velocity, where t is in seconds. If the radii of the gears A and B, so you got two gears inside. You can't see them as easy in this image. So there's a gear A and a gear B. The radii in gears A and B are 0.25 inches and 1 inch respectively. Right, so it's a 4-to-1 between the two gears. Determine the magnitudes of the velocity and the acceleration on tooth C on the saw blade after the drive shaft rotates theta equals 5 radians, starting from rest. So there's a few things we need to sort out from this problem. Like I said, this is the gears behind the blade. So if you think of the blade on one side, we're seeing translucent gear A, gear B, and gear B and the blade both share a hub, and that's where that bolt is going through. Let me change this and make this a pointer. So that's where that bolt is going through. So on this free body diagram, we have gear A, which is tied to the motor. The motor actually comes through on gear A. That's where the power is coming from. And here we have gear B. And since it's got the same center as the blade, here we have the blade, which is C. And I'm saying the tooth is out here, right? 2.5 inches radius. So 1 inch radius on gear B and 0.25 inch radius on gear A. And this is the information from the motor. So omega sub A is this function 20 t raised to the 2/3 radians per second. And theta, we're looking at this whole thing when the rotational displacement is 5 radians. So we've got a start at 0, then move to 5 radians. So we're looking at all this when this whole drive shaft, which is running through here, is going at 5 radians. So what is this doing here at C, this tip of this blade, once this has traveled through 5 radians? So what we're doing, that we have here is we've got two gears tied together with a common tangential velocity. And we've got one gear and the blade, the second gear and the blade, gear B, and they have a common rotational velocity, because they share a common center, a common point of rotation. So that's kind of setting up the problem. So now let's go ahead and take down all the key information. So here we got the function that defines that angular rotation of the motor, the angular velocity of the motor, excuse me. We've got the radius of gear A, the radius of gear B, the radius of the blade, C. You start at theta equals 0. So theta, not theta, is 0 radians. And the final is 5 radians. And keep in mind that gear A is the driver. All right. We're trying to find the magnitude and the velocity of tooth C. So the magnitude of the acceleration and the velocity of tooth C on the blade. So here we have V sub C, the tangential velocity of that blade, and the normal velocity, or excuse me, normal acceleration, and the tangential acceleration, again at C, and then this would be the magnitude. So we got 4 things that we're trying to accomplish. So now we've got the problem laid out, or I got all the information. Now let's work through our thought process. How are we going to get from this point of all this information on gear A and get it to this tooth? So let's go ahead and write through our thoughts, or I'll put out our thoughts on this. So first thing, gear A is the driver, right? And the angular velocity is expressed as a function. They gave it that as a function, and it's a known displacement So from 0 to 5 radians. And we've been given all of our radii, all the radius, right? So that's the driver. We've given the angular velocity as a function, and we have a known displacement that particular gear goes through. So that's all laid out there. Now we also know that the functions, for acceleration can be derived through this. So the acceleration, the angular acceleration for gear A, we can derive that as a derivative of that function with respect to time. And we can also get a better understanding of displacement by treating it as a derivative or the angular velocity as a derivative of the displacement with respect to time. So those are key information. That'll give us functions for, some information for our displacement. We'll find out what the time is, and we'll find out a bit about the acceleration just through doing derivatives and integration. And we also know that this was something from a past video where we talk about the relationship between gears. When they have a common point, a tangential between them, gears in mesh, they have a common tangential velocity. And once we, accept that relationship, we can use that to translate to the rotational traits or rotational functions of the mating gear, using that tangential velocity as kind of the bridge. So once a function has been derived for angular acceleration for gear A, so once we solve everything we need for gear A, gear B can be addressed through a common tangential velocity and the acceleration. And that's where these equations are going to step in. So we've got a angular on the right side of the equation. Omega times r is equal to the tangential of v. And tangential velocity of acceleration is the angular acceleration times the radius. And the normal acceleration is equal to the angular velocity times r. And that should be an a, not an alpha of sub n. So we have all the conversions, all the equations we're going to use to convert. And we understand that the tangential acceleration of A is equal to the tangential acceleration of B. So same here, the tangentials are going to be the same, as well as the tangential velocities are going to be the same. So that's the relationship that's going to pull us through. So again, this information can be used to derive the information on the blade C, because of the common angular velocities and acceleration. So once we know what's going on with B in terms of tangential and converting that back to rotational angular, we can then expand that out to the blade. And again, the only difference, they've got a common angular rotation and angular acceleration, but they have two different radii. So we'll use that to get all the information going through this tip. So we'll find all the information rotationally on A. We understand that these have a common tangential, so we can use that to find all the information for gear B. And then since these have a common center, we can use that information to find what's going on tangentially at the tip of that blade. So now let's start putting this together. Starting here. So first we're just going to derive the functions that represent the angular displacement and the acceleration. So that'll be the easiest thing we can do. It's just starting with gear A. So when we look at the displacement, that was a separable differential equation, and it's a definite integral going from 0 radians to 5 radians, the displacement. And we've got an interval of time that we're concerned with. We don't know what that is yet, but omega dt, we integrate both sides. We do our substitution, integrate both sides. So this just is theta final, or theta at 5 radians from theta at 0. And on the right side of the equation, to do in that integration, the constant comes on the outside, add 1 to the exponent, end up with 5/3, divide by the new exponent. So you end up with 60 over 5, or 12t raised to the 5/3. And now you can just solve for t, and you end up with 0.591 seconds. Again, so you're solving for t. Divide both sides by 12, and then take everything to the cube root and to the fifth, and then you end up with 0.59 seconds. Now that we've got a time, 0.591 seconds, and we have a function 20t to the 2/3, now we can figure out what the velocity is on A, the angular velocity for that. Just plugging in that window of time, or that point in time, and we end up with 14.091 radians per second. So that's the angular velocity for A. Now we can also now start to look at the acceleration. So we know that acceleration is just the derivative with respect to time. So we take that function of 20 times t to the 2/3. The derivative of that is, basically 2/3 times, 40 over 3 times t raised to the negative 1/3. So you're, multiplying by 2/3 and subtracting 1 from the exponent. And now you can take that same window of time, 0.591 seconds, put it into this function for acceleration, and you'll end up with 15.885 radians per second squared. So what we've done now, we've got all the rotational information for gear A. So we just put this over to the left, and now we can start looking at what's going on between gears A and gear B. What's happening between gear A and gear B is you have a common tangential velocity between both of them, and you've got a 4-to-1 difference in radii. So this one is fairly straightforward. The tangential velocity of A and B are equal. And for A, it's omega A times R. And for B, it's omega B times R. And let's see, we know all this information. We know the radius of B, we know the radius of A, we know the radius, or the angular velocity of A. We calculated it at that point in time. And we can solve for the angular velocity of B just by dividing both sides by the radius. And here we have, go ahead and just do this here, make this a pin. Our inches cancel. And what you end up with is 14.091 times 0.25 radians per second. So you have 3.523 radians per second. So now we've got an angular velocity for the gear B. So now we can start to look at, we know it's got a common velocity, common angular velocity between gear B and C. So now we can take advantage of that relationship. So omega sub C of the blade is equal to the omega sub B of gear B. And that means we can just go ahead and substitute the tangential, or substitute that in multiplying by the radius of the blade. So now we're taking this velocity that we've calculated, angular velocity, multiplying it by the radius, since those are two common, and you end up with a tangential velocity from here going down at 8.81 inches per second. All right, so now we've got all the information that we can translate over from gear B to the blade, and we can now start looking at the acceleration. So let's see, we've got all this information. We can go ahead and move this over and capture that. Now we can start moving forward here. Like I said, gear A and gear B have a common tangential velocity. So that means we can get our acceleration the same way we got our angular velocity. Again, those are common and they're based on the radii. We have all these are known. Here, the radius is known, and the radius here is known. We just don't know this angular velocity, or angular acceleration for gear B. Divide both sides by the radius of B, and you end up with 3.971 radians per second squared. And that's for gear B. which is also the angular acceleration for the blade. So gear B and the blade have a common angular acceleration. So now we can use those to get our tangentials. So let's see, our tangential for gear C would be our angular acceleration for C times the radius of gear C. So that'll be our tangential, which would leave us with 9.928 inches per second squared. So again, at the same point at C, that acceleration is going to be 9.928 inches per second squared. That's the tangential. And now we have to find the normal. So we got the acceleration in the normal for the blade is equal to the square of the angular velocity times the radius. So we calculated this before. Over here, we calculated this before. It's squared times the radius of 2.5. You end up with a normal acceleration of 31.029 inches per second squared. So now we've got a tangential acceleration and a normal acceleration, and we do have a tangential velocity. So now we need the magnitude of our two accelerations, which is the root sum square, and we'll have to be done with everything we know. So we have everything calculated and put away. So now we do that final calculation. Let's see, we have our accelerations, and we can look at our two accelerations squared, tangential and normal. They're squared, summed, and the square root gives us our magnitude, 32.6 inches per second squared. Yeah, this is Professor Cummings. I hope that was helpful. If it was, go ahead and like the video. Look and leave a comment or ask a question if anything else you want me to discuss, and I will talk to you in the next video.